been fun. I'm really sorry, Johannes. Before I get into it, can I ask everybody to give a round of applause for Johannes and everyone at DLR today? This is truly special. It really is. So, thank you.
I thank to the others to get in.
Thanks to the others. Yeah, so my name is Joseph Sullivan. I'm a fifth-year PhD student at the University of Washington, advised by Sam. I have this poster I'm going to be showing on Friday. It's just a quick preview. It's work that I've been doing for a while with Sam and students in Aaron Johnson's lab. We've been working on designing multi-behavioral robots using multi-objective optimization theory, and in kind of an extreme edge case, designing a leg to be also used as like a limb for manipulating objects. So we optimize the passive mechanics of this thing with parallel elastic elements, and we show that you can kind of generate a bunch of designs which do better than sort of the vanilla leg, which we took off of a Minotaur essentially. But today I want to focus on something that's more relevant to you guys, which is locomotion. But I'm an engineer, and like this engineer here, when I'm working on a problem, I constantly am weighing competing objectives in my mind. So I have to balance things like how much energy density I'm going to have in the system, or power density is it going to have, what does it weigh, how fast does it go, if it's a legged robot, can it go 3 meters per second, and what's it going to cost? All these kinds of things, I think we just sort of subconsciously make trade-offs, but often a lot of time we're thinking explicitly about them. But I want to advocate for people to more often try to systematically explore the trade-offs between their competing design objectives, and so that's kind of the theme of this talk. So when we're designing legged robots or we're designing robotic prostheses, there's a lot of things that we have to weigh. So we have to make choices like, what type of motor am I going to use? What size is it going to be? Is it a brushless DC? Is it a harmonic motor? Am I going to use linear ball screw type things? Also, over the years, we've seen a lot of talks where compliance plays a really big role in the design of robots, whether that is for storing and returning energy, or protecting the motors from impacts in series elastic elements. And two more really important ones are, what's the gearing that I'm going to use? How do we build the transmission of our robot? So, like, how do we optimize the geometry of our linkages and the transmission and things like this? All these things are constantly in our head, and it's most of the time we sort of exercise our engineering judgment and come up with decisions that we think are rational, that we think make sense. But I don't think often enough in papers in the academic environment we're seeing like a full exploration or justification of why we make some of these choices. And I think that multi-objective optimization theory can really help in this respect. And so, to illustrate that, in the multi-objective optimization context, there's a lot of designs which are good, and that you can't say they're strictly better than others. So like, for a prosthetic hand, the hook hand is really cheap, it is useful. The robotic hand is very sophisticated, it's more dexterous, it has better capability, but it's more expensive, maybe it weighs more. But there are some things you just shouldn't do. So if you're going to make a prosthetic foot, don't put like a rollerblade wheel for it, right? Like you're probably better off, you can more cheaply like make a wood carving and stick it on the end, and it's going to work better. And so this is just to illustrate that like there are designs in our design space that we need to eliminate, and so that we're only considering the things that can justify in some sense. And in this, yeah.
What's wrong with the rollerblade?
I think you're going to get hurt. I don't know. Yeah. So, but the challenge is how do we operationalize eliminating the bad designs and winding up with the good designs that we want to consider in more detail. So to this end, multi-objective optimization can really help us in certain contexts. And so in multi-objective optimization, I maybe have multiple cost functions, like the one on the left, which is sideways, and the one on the bottom, and that when you plot sort of the costs for both of these in one Cartesian plane, you'll see that most of the designs which are up and to the right are bad. That's in red. But there's this nice like green curve, and those are good designs. We call that green curve the Pareto front. And what it basically is it's just a set of all the designs which aren't strictly beaten in every objective by some other design. So really, I think that when we're designing these systems, this is the set that we're trying to refine our design space down to, and then we can really start diving into the decisions or maybe exercising more engineering judgment. But to systematize this, half the battle is going to be, how do I even write out a cost function for my objectives so that I can like find this Pareto front to begin with. And it's not totally straightforward, but to take a step back first, if we're going to refocus this on just legged locomotion, which obviously is the most relevant thing to this community, one really common objective that we've seen in many talks is cost of transport. You know, how long can my robot run on a battery? How much metabolic energy is a person expending when they use this device? Those things are going to determine their endurance, their power autonomy, how long they're able to operate. And also, there are many different locomotion behaviors that are considered in the dynamic walking community. So just for bipeds, you know, you have walking, running, ramp ascent, descent, stair climbing, etc. So even within these different locomotion tasks, when we're designing a system, we could try to induce a multi-objective optimization problem that balances the trade-offs between these different behaviors. But what I actually want to get into is that each gate is really a continuum. Each individual gate is a continuum of behaviors. So this is a really, figures from a really cool paper that had a lot of influence on my thinking from Gan Zhenyu and Dave Remy back in 2018. And what they showed is that all of the gates of biped can emerge from just carefully chosen initial conditions of this conservative mechanical system. So each one of these lines in this like 3D plot, basically a colored line is like a type of gate. And all of those curves are different initial conditions or different fixed points on a Poincare map that determines like what's the speed that it's moving. Is it going forwards or backwards? How high, how much height does it gain when it's walking? And so I really want to emphasize that even if I took an individual type of locomotion behavior, we can actually begin to reason about, is this system a good general walker or general runner in the sense that we maybe want to be good at multiple speeds or multiple ramp angles, etc. And so how do we begin to capture functionally what the performance of our system is going to be subject to our design decisions? So now it's math time, and I'm really sorry, but we've got to do math for this. So I really like to take the template and anchors kind of approach to thinking about this problem. So many of these behaviors we see emerge as sort of passively stable or not stable, but still periodic solutions to really simple reduced order dynamics. So we're going to have some template state space M, and then we're going to have Rn just be like the set of design variables that we're going to consider. So like we have n design variables. And so the thing that we're really interested in is a certain subset of the periodic orbits of the system that's going to represent like different instantiations of a gate, maybe different speeds or stuff like this. And so the thing that we're looking for is some function which is going to map your periodic orbits and your design variables into the real numbers that somehow captures like performance. In this case, maybe metabolic costs or energy efficiency and locomotion. And another neat thing that we can do is we have a bunch of these orbits for each gate. So if we can find a measure function, so basically this is just like a function that you integrate over all those periodic orbits and that integral sums to 1, then we can do something really cool, which is that we can derive a single cost function which sort of encapsulates all of the different gates within an individual locomotion behavior. And so we have this weighted integral now where rho sort of scales the relative importance of each gate in the set of periodic orbits. And then if we can minimize this thing, then what we're going to end up with is a Pareto efficient design which is subordinate to that weighting that we chose. And I'm not going to get into exactly how you choose the weighting. I don't have the exact answer to that, but maybe we just evenly weight them or something like that. But what I want to get down to is what should this function that represents the performance of an individual orbit subject to my design decisions, where does it come from or how might we derive such a thing? So if we're going to take the template and anchors approach, we'll take a step back and we'll look at the anchor space. So we have maybe some complex robot that we have a plan, a schema of what it's going to look like. Maybe we've chosen the type of actuators and where compliances might be, but we haven't figured out all the geometry and the size and the gearing, etc. And so now N is going to be our anchor state space, and if we have some injective mapping that's going to make the orbits of our template model, our template gates, into orbits of our anchor space, so an injective immersion, and we have a cost function that maps the anchor orbits and the design decisions into the real numbers, then we can construct our cost sort of term in the template space by passing basically the template orbits through this immersion and then doing the calculation effectively in the anchor cost. And so one way that this makes this easier is that a really common cost that we might use if we're doing trying to optimize our energy efficiency, for example, is maybe we compute the L2 norm of the controls that we need to realize that orbit in our system. So this is sort of like an idea that I've been kicking around for a while. It's one part of the poster that I'm going to talk about on Friday, but I just wanted to show it to you all and pose a few open questions. So one thing that I don't know the answer to, and I'd love to hear people's thoughts on, is that usually the dimension of our template, like as a dynamical system, is lower than the dimension of our anchor system, of our actual robot. Like it's simpler in some sense, there are fewer state variables. And so a challenge is, if we need this immersion to sort of map our gate, our template orbits into the anchor space so that we can compute the performance, what immersion do we choose? Because there's many different ones. And so it's not clear to me what the answer to that is. Or conversely, if we take the opposite perspective. So instead of an immersion, we consider a submersion. So we're basically projecting all the possible anchor orbits into the template orbit space. Now we have this problem of, okay, we needed this measure function rho in order to weight all the different gates of a walking or a running behavior together. And the question is, how do we then lift that measure into the anchor space? I do not have the answer to this, but I'd love to hear people's thoughts. And finally, I also am really curious about how you handle this scenario when the system is under-actuated or you have constraints on your control bandwidth, because maybe the template orbits aren't actually totally realizable. And so perhaps there's a trade-off between the accuracy of anchoring your trajectories against the energy efficiency itself. So yeah, that's the gist of my talk. So yeah, open up for questions. Yes?
So the biggest thing that comes up for me whenever I think about this stuff is like, so many of the design choices you have are not continuous variables. It's like, how many legs should your robot have? Or, you know, like, which of these 5 motors should I choose, right? There's all these things that are like integer flavored.
Yeah.
So what do you think about that?
Yeah, I mean, so it's a challenge, right? Once you have integer or binary variables, now it's less straightforward to solve because you're not going to just be able to use techniques from smooth optimization. Like you're going to get into, you know, it's an NP harder problem at that point, and you maybe need to do branch and bound, or you have to decide before you design your robot, like here's the general schema that I'm going to consider in my class of design. So restricting it to choosing a priori what type of actuator, what type of linkages, and like where the compliance goes. So that's an excellent point. I think that's the thing. At one point or another, we either may need to exercise engineering judgment before we explore or try to generate the Pareto front, or we have to do a lot more work and fall back on more sophisticated systematic tools in the case of like mixed integer programming. Yeah.
It's not great.
Yeah, it's not great.
Doesn't it your measure get easier though if you do it in discrete space?
I don't know.
Just do a counting measure.
But what about the continuous variables? Or are we going to discretize all the design variables, I guess? Yeah, that's an interesting perspective I didn't think of. Yes?
I mean, I'm going to, you know, setting aside all the integer variables, you know, I've fallen down the rabbit hole in the past, and I wish you better come up than me, of trying to optimize a morphology while also minimizing the cost without thinking the generality, and the results were hilariously stupid. And so, but like, it's like even just the simplest walking task. But like, is there like a toy problem that would like really exemplify a successful thing? You give us a lot of general examples.
Yeah. So in my poster, if you come to it on Friday,
Okay.
I will show you an extreme toy problem that we're working on right now. We've built out in real hardware, and now we're just working on like getting the controls in place.
Okay.
So yeah, absolutely. But basically, the spoiler is that we build a leg both to be a hopper that can hop energetically efficiently, but then also if you rotate it into its workspace, it can support like heavy loads and provide nice smooth even control, and it has superior endurance in both of those behaviors than just a back drivable leg with no parallel compliant elements.
Thank you very much.
Great.